You ready? Start recording. In today's video, okay, there's no cameraman behind my camera. I'm just pretending like I've got some help and it's not just me sitting here on my own on a Sunday morning staring into that camera lens. Back to reality. In today's video, we are going to be talking about chilled water system pressure control, and more specifically, where do we install the system pressure transmitter? This is a pretty easy question, and the answer is pretty easy too. Most people follow the rule of thumb that the system pressure transmitter is installed 3/4 down the pipe run from the pumps. As the plant room, 10 floors down, that's where we install the chilled water system pressure transmitter. Some people say 2/3, 3/4, I think it's pretty much the same thing. However, a few years ago, I worked on a project where the BMS company had installed the pressure transmitter 3/4 down the run, and it didn't work. And while we're doing BMS witnessing, we were doing the chiller pressure control and the bypass minimum flow control to the chiller, and it wasn't really working very well. There were problems. So we actually ended up having to install a second pressure transmitter and bypass valve in the plant room quite close to the chillers, which is really the opposite of what we all believe we should be doing. So in today's video, I'm going to sketch out on a piece of paper that exact, or very similar, how I can remember it, that building and that chilled water system, and explain to you why 3/4 was the wrong position. And then through that discussion, what we're going to do is we're going to try and find a better rule of thumb than simply saying 3/4 down the run, because 3/4 down the run doesn't always work. This discussion, I'm going to be talking about chilled water systems. It obviously also applies to heating hot water systems, and a lot of the principles that we'll talk about do also apply to air systems, for air handling units, your AHU supply fan. How far down the run do you install the pressure transmitter? The rule of thumb is 3/4. Do we need to reconsider that? I don't think it's as sensitive as the chilled water system and hot water system, but it's, same sort of thing. Alright, so with this building, this was a VAV type of building. So we had, I think there was around about, this was a university, there's around about 8 levels. So we had a 7-story university teaching building, and the level 8 was the plant room. We had 2 chillers, primary only pumping. We had all of our air handling units in the roof plant room. The north air handling unit, the south air handling unit, east, west, center 1, center 2. So if we had a little drawing of the floor plan, this is a top view of the floor. In the middle here is the core of the building with the lifts and the toilets and all those sort of things. And on the end here we have our services risers. So north, south, east, west. So our north air handling unit would serve all the VAVs in the north. Our south air handling unit serves all the VAVs in the south. East air handling unit, west air handling unit, center zone 1, center zone 2. So across all 7 floors, each AHU does one of the 6 zones: north, south, east, west, center zone 1, center zone 2. There's our AHUs. Because it's a VAV system, we don't really have chilled water on the floors. The hot water system might have some hot water reheats on the perimeter here, but for the chill water system, we basically had our big air handling units serving the air down onto the floors, and at the bottom here, we had a couple of fan coil units, or 3 fan coil units. So, and this is probably a reasonably typical type of building for when we don't have chilled water on the floors. So let's say, for example, this pipework was about 150 millimeters. And then perhaps, down here on the same level in the plant room at the last air handling unit, maybe the pipework was, a little bit less, so it'd be 100 millimeters. And then, there's not much cooling demand down here. So down here on our fan coil units, the fan coil unit's probably only 15 millimeters. The fan coil unit pipe. 3/4 down the run of the system, this plant room's together, it's not that big, and there's a run down the riser. So where we'd installed the pressure transmitter and the bypass valve, let's say here's 4/4, which is the full length. Halfway, it's about here. It's about halfway on the pipe run. So 3/4 would be around about here. We had, this is where we had our pressure transmitter and our bypass valve. So that's supposed to be a flow and return. It's not very clear, I guess. So here's our system pressure transmitter controlling the speed of the pumps. Here's our bypass valve controlling the minimum flow through the evaporator. So there's our differential pressure transmitter across the chiller. Probably got one this side too. Not probably, there would be one this side too. Could have flow meters over here. We're going to have pressure transmitters for this example. So you would think that from a design point of view, this is the correct way to install the pressure transmitter bypass. So the pipe over here is, this pipe 15, 20, let's just guess and say that over here, the pipe is 30 millimeters. 150 millimeter pipe in the plant room of the pumps. Pipe size reduces down to 100 by our air handlers, drops down this riser. Because we don't have chill water equipment, we don't have chill beams or fan coil units on the floors, this pipe is only sized for the load down here. It's a small pipe, this. So when they did the chill water system balance, and they opened up all these valves to be, the VMS valves be fully open, the control valves, and these 3 fan coil valves be fully open, and they set the pump to the design speed, so the design volume of water through here, and the whole thing was balanced and perfect, with the correct design flow rates through each coil, a bit more here, a bit less there, with the correct design flow rates through our fan coils. The whole system was perfectly balanced. At that point in time, maybe we had 30 kPa down here. 30 kPa. So 30 kPa becomes your set point for your pressure control. So we had a PID loop, system pressure, controlling the speed of the pump. We've got a set point, we've got a proportional band, integral time, blah, 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 it's PID loop, measuring the pressure, controlling the speed of the pump, and then the bypass valve. The bypass valve controls the minimum flow through the chiller. PID loop, process variable, output, set point, proportional band, interval time, etc., etc. So that's the system. Now, at this time that we're balanced, everything's sitting perfect, and we've got 30 kPa here, and the system's balanced. The pressure up here is obviously going to be much higher. So let's say that the pressure around about here, the pressure up there, 150 kPa. So at balance, our transmitter reads 30 kPa, it's 150 kPa there, and maybe the pumps are discharging at, maybe 200. So there we go. So here's the first problem. This transmitter will work. This will work because as the load in the field starts to decrease and the VAVs will back off and these chorder valves start to close off and the system pressure starts to increase here, the system pressure increases from 150, it increases up. At that point in time, that pressure increase will actually probably be detected here and the pressure will go up 35 kPa, 40 kPa, and the pump will slow down. So putting the pressure transmitter here, the system essentially, fundamentally, it will actually work. The same thing is if you actually install the pressure transmitter up here, it would still work. They would get a set point of 200 kPa from the water balancing guys, and we'd control to that. And as these AHUs start to back off and these two-port valves start to close and the pressure goes up, that increase of pressure here will also result in this pressure also going up and the pump will slow down. So in the most basic terms, you could almost install the pressure transmitter anywhere. I've actually seen packaged pump sets come to site with the pressure transmitter actually installed off the packaged pump set as a packaged system. This was in the UK a very long time ago. And I didn't actually check it, but maybe it works. Let's just forget about that for a minute. But what I'm trying to say to you is, as things are closing off in the field and the pressure's changing, that pressure does sort of make its way through the system. You do detect and it does slow down. But here is the key points that I want to make. If you watch those previous videos on valve authority and equal percentage, maybe go and watch them if you haven't watched them, where it explains that with two-port control valves, variable volume systems, which we mostly have, the valve authority equation is different to the three-port. Let me just touch on that for 2 seconds. Let's take our East air handling unit and just expand that drawing slightly. Just bear with me, I actually am getting to something. So here's our East AHU. Now, with a three-port system, like we had a very long time ago, the valve authority formula only requires you to have the pressure drop across the fully open control valve, and the formula requires the pressure drop across the coil. Now we have those pressures, and we discussed this I think in detail, I can't remember, in those other videos. We need to know this, but with a two-port system, the valve authority equation is not the same as the valve authority equation of the three-port system. For a two-port system, the valve authority is the pressure drop across the valve, and the way it's described in books and on the internet is it's the rest of the circuit pressure, which I think is this pressure here, but I might be wrong. Probably not. So you can see that with a three-port system, the point I'm making here is the system pressure of the local branch there is what determines the valve authority and good control over the system. So what we should be doing is, when we balance the system, we should be installing our pressure transmitter not 3/4 down the run, but we should install our pressure transmitter in a location that best represents the load. Here is the load here. This is a good representation of the load for this building. This is not the best representation for the load of this building because we don't have chill water stuff over here. If we had plant rooms all the way down here with AHUs in here, yes, then that would be the best location. So when they do water balancing and they give you that set and you use that set point of 150 kPa here and not the 30 kPa here, it means that your pumps are always controlling to maintain the pressure correctly at the point where the load mostly is because of this, how you calculate valve authority. See here, if we can hold this pressure correct here, then we're holding the correct valve authority, although we don't know what the number actually is in real life. So again, if we hold the pressure here, we're sort of trying to get the pumps to hold this area here. Because when it's properly balanced and everything's open and it sits like this, the 30 is sort of okay, but Every other day that's not full load, here in Melbourne, Australia, we probably only have a design day, where it's over 35 degrees Celsius, probably like, let's say 5 times a year or something, or 5 times through summer. It's not the normal. So when we're not in full load and the valves aren't fully open and they're open to all sorts of different amounts and there's different things going on in different places, this pressure here probably is not a true representation of what's going on over here. So the design of where you put your system pressure transmitter, it's not just about how well the system will control. How will you have stable control to the pumps and reliable control and blah, blah, blah. It actually has a lot to do with where do you want to have the right pressure. Do you want to have beautiful pressure down here? Or do you want to have good pressure where the main equipment is? Now, just quickly while we're on this little topic, let me just do something else. Let's say, for example, you are on a building that had multiple chill water risers. So 1, 2, 3 risers plus that plant room. This maybe is a big building. So there's things happening down here off these risers. Maybe you have a lot of fan coil units. Maybe you have lots of chilled beams. Here in Melbourne, some of our consultancies like chilled beams, so we do get them here sometimes. Where does the system pressure transmitter go? So when they balance this system, maybe sort of 50 kPa over here. When they balanced it, maybe there was 50 kPa over here. In the perfect world, you would actually have a pressure transmitter in each riser. It's probably getting a bit messy here. Apologies, guys. And there, so you got 1, 2, 3, 4 pressure transmitters. And when they do the balancing, and the mechanical water balancing technician says to you, okay, look, I've gone to where your transmitter is, and I've measured 50 kPa there. In fact, you could just look at your BMS. When they say to you, hey guys, water balancing is finished, everything's open, it's all perfect, you could just look at your pressure transmitters and write them down, 50 kPa, 40 kPa, you'd write these values down, 50, 40, 30, 150, you'd write them down. And then what you would do is, when the system goes into automatic mode and everything's moving everywhere, you would look at all those pressures and maintain the speed of the pump to ensure that the lowest pressure was on set point. So if you're controlling to here, if this was the lowest one, these are all opening up. Let's say this is on the north side of the building here in Australia, and the sun is shining onto the north facade of the glass. These fan currents are going to be in full cooling maybe. So their chiller valves are all fully open. This pressure could be quite low. So we need the pump to push this pressure up to hold the design here so that the valve authority is correct for the fan coil units. That would result in this being a little bit too high, a little bit too high, a little bit too high. But at least you have enough pressure everywhere. We're not starved of pressure. Look, I hope that made sense because, yeah, like it's a bit, that sketch is a bit messy, but you can certainly get the idea of what I'm trying to say, that the location of the system pressure transmitter is very important, and you might need more than one of them. That's really important. And the second thing that I want you to sort of get out of this is you might have, hundreds and hundreds of different sensors on your project, pressure transmitter, CO2, CO, humidity, everywhere, like hundreds of VAV boxes. And things like this, the system pressure transmitter, can easily just get sort of forgotten about with all the noise going on with you trying to design this building management system or whatever it is. But this one thing is very important. It affects the entire chill water system and the hot water system sort of thing. So you need to try and spend a little bit of extra time thinking about this one sensor and its location. When I was drafting this out this morning, there's a whole bunch of things that I started remembering, like the lessons that I've learned over the last 20 years. Because what I've explained to you here is the theory of how we should do it ideally. But those of you that work in construction know that it's rare that you have a situation where you have enough time and money to build something perfect. That doesn't happen. So I might do a second video where I'll run through some of the lessons that I've learned, the issues I've had, and how I had to adapt my design. Because sometimes you have to compromise. You think, you know what, I want to put it there, that's the best spot. But there are some other negatives around putting it in the best spot. I have designed systems where I've installed transmitters in not the best spot, because the best spot for control had other issues that came with it, other sorts of coordination issues, health and safety issues, whatever it is. So I might do that in a week or two if I get around to it. The other thing is, this is a bit of a secondary thing, but when I started my career, as a project engineer, blah, 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 and doing software and installing servers and SQL and all that sort of stuff, we all love that stuff. And in around 2006 or so, I went from service small projects into core system design. I did that for about 4 years at least. And what I noticed was that I wanted to continue growing in software design, but I was learning more and more about hardware design, control panel design, variable speed drives, these sort of details. And believe me, we have scratched the surface today about the system pressure transmitter. There's a whole bunch of very important things related to this, which we may or may not talk about another time. But I was struggling to keep up with Microsoft and in those days Java and those issues in software design, and to keep up with hardware design and learn. And I looked around me, and all the design engineers that were in London at that time, because they enjoy software, were following up on software design. There's only one guy that had focused 100% to be a hardware design specialist. And I came to the conclusion, from my own personal opinion and experience, is that hardware design is more important than software design. That's my opinion. If you've got something installed in the wrong place, or the wrong size of valves, or the control panel, you can't fit the controllers in there, those are big problems. We can always fix software on our keyboard later on. We can fix software problems. What I'm getting at here, because sorry, I'm rambling a bit. This discussion is not actually in my notes. I'm just making this up. That's why it's not getting to anywhere. Sorry. What I'm trying to say here is, you guys as young BMS design engineers need to try harder and focus more on hardware design. I see that this skill over the last 20 years is being lost. I guess also, to be fair, when I was a young engineer, we didn't have 200 electric meters. We didn't have all these water meters, loads of gas meters. We didn't have thermal meters. We didn't have high-level interfaces to 20 different things. We didn't have hundreds of variable speed drives. We didn't have complex integration. So I appreciate that nowadays software design is much more complicated than when I was a design engineer. But I think that this next generation of engineers are not really focusing enough on hardware design. We're focusing on software. And this was the second part of this video. The first part, as I said before, was where to install the transmitter, blah, blah, blah. That was just like the technical detail of the discussion. But the second part is for you to understand that even something as small and simple as a pressure transmitter, it's very important. You need to spend an extra 2 or 3 hours on this one transmitter. I had to spend a couple of hours with the schematics and working out where it should be, then go to site with the layout drawings, the pipe work, and there's the pipe. I thought that was the best spot. That's not the best spot, because there's something over there. It's above a door, and they've got to get a ladder up to get to it, so I'd go put it somewhere else. So we have to try harder with hardware design. It's very important. Now, my last thing I want to say was, I'm about to wrap this up. Just bear with me if you're still here. This morning, I started to plan this video at around 7 a.m. It's 11:45 now. I spent the whole morning, almost half a day. It took me 2 hours to draft out, I first drew this drawing out, as a concept of, so I had an idea of what I'm going to say. And then I wrote out 2 pages of stuff to try and say. I spent at least an hour fiddling around with my lights, setting the room up, those things there. This thing was a flippin' nightmare, this thing. Test that, those settings, blah, blah, blah. My point is, I don't earn any money doing this. This is a lot of effort for me. So go and buy a notepad, watch these videos. If you learn something, write it down and promise yourself that you're going to try and change something in your workflow and improve something, because this is a lot of effort. So when I say to you, please like and subscribe, I say that because that's how I get feedback that you people get some value out of these videos, and it motivates me to make more videos. To make money on YouTube from advertising, you need like 1 million subscribers. We probably don't have 1 million BMS people probably. So this channel, the effort I put in here, I actually worked out last year that I spend about a month, 100, 200 hours, not exaggerating, 200 hours a year on these stupid videos. So I'm investing a lot of time here. So please, like, try and learn something from it and try and make a change and improve your workflow and get something out of it, because this is a lot of hard work. Like and subscribe, and we'll see you next week or the week after. Maybe I'll do a second video.